Okay, we're now discussing section 2113, the Doppler effect for electromagnetic waves. Let's get to the PowerPoint, go to the next slide. And as you remember, sound waves exhibit the Doppler effect when the observer, the source, or both are moving relative to the medium or medium of propagation. Recall that in the Doppler effect, the observed frequency of the wave is larger or smaller than the frequency emitted by the source of the wave. A Doppler effect also occurs for electromagnetic waves, but it is different from the Doppler effect for sound waves in two ways. First, in the Doppler effect for sound waves, motion relative to the medium is most important because sound waves require a medium in which to propagate. In contrast, the medium of propagation plays no role in the Doppler effect for electromagnetic waves because the waves require no medium in which to propagate. So as shown in the bullet, sound waves require a medium, E&M waves do not. Second, the speed of sound that appears in the equation of the Doppler effect for sound depends on the reference frame in which it is measured. In contrast, as we'll see in a later topic, the speed of electromagnetic waves has the same value in all coordinate systems that are either at rest or moving at constant velocity with respect to one another. The single equation that describes the Doppler effect for electromagnetic waves is given by the approximate expression here. F observed is equal to F of the source times 1 plus or minus U over C if U is much less than C. F sub 0 is the observed frequency. F sub S is the frequency emitted by the source. U is the relative speed of the observer and source, and C is the speed of light in vacuum. Note that this equation is valid only if U is much smaller than C. It can also be used for sound as long as the relative velocity of the source and the observer is much less than the velocity of sound. The positive sign in the equation must be used when the source and observer are moving toward each other, and the negative sign must be used when they are moving away from each other. From this, we can anticipate an increase in the observed frequency of the source and observer if the source and observer are approaching each other, and a decrease if the source and observer recede from one another. Astronomers have made important discoveries using Doppler observations on light from distant galaxies. These measurements have shown that the more distant a galaxy is from Earth, the more its light is shifted toward the red end of the spectrum. This cosmological redshift is evidence that the universe is expanding. The stretching and expanding of space like a rubber sheet being pulled in all directions is consistent with Einstein's theory of general relativity. A given star or galaxy can have a peculiar motion toward or away from Earth. For example, Doppler effect measurements made with the Hubble Space Telescope have shown that a galaxy labeled M87, shown here, is rotating with one edge moving toward us and the other moving away. Its measured speed of rotation was used to identify a supermassive black hole located at its center. And with that ends the chapter discussion. That is the last that we'll be discussing for this second summer session, and we'll end it right here. All right.